So our next speaker is Julie Stopar. Julie, you can go ahead and share your slides. And Julie will talk about MARE deposits in the AUSTRALE region of the moon. So I reset the timer.
Okay, thanks. Before I get started, I wanted to acknowledge my co-authors as well, Sam Lawrence, Carolyn Van de Bogert, Harry Hiesinger, and Thomas Jaguar. They've all worked with me on this project for a while, and we've had a great time. This work is supported by the Lunar Reconnaissance Orbiter and camera teams, so I want to thank them as well. So MARE AUSTRALE, it's this area on the southeast limb of the moon, right where the star is, between 30 south and 65 south. And if we just peek around the limb a little bit, we have a better view of it. Here is MARE AUSTRALE. And now you can see that it's roughly circular. It has a low albedo. This area is about 900 kilometers in diameter. And it's been proposed that this is potentially a partially filled, MARE-filled impact basin. However, the more recent gravity and topographic information that we have now doesn't really support a large basin across the entire Austral region. But the work of Newman et al. In 2015 does suggest that there's a smaller degraded basin in the north. It's about 600 kilometers in diameter. But that does leave a broad scattering of smaller MARE deposits to the south that aren't associated with it. And so it also leaves a question as well about, is MARE AUSTRALE a good analog for the early stages of basin eruptions, the ones that infill them? These would be things that would be obscured in basins like Imbrium or Serenitatis by later massive lava flows. There you go. So in this work, we utilized the newer high-res imagery, the topography, composition, and gravity data to update the crater size frequency distributions, derives new surface ages, and investigate the stratigraphy of the area. And of course, our ultimate goal is to understand the timing of the volcanism here and how it relates to any basin structures. So as I already mentioned, the newer elevation data, and this is the SLDEM 2015 model shown here, they don't really support a large basin across the entire MARE AUSTRALE deposit region, but we do see a topographic low in the north where the smaller basin has been proposed. And the other thing to note from the topography is that even closely spaced MARE deposits can have highly variable elevations. So like the three right here span a pretty wide range. And there's also in the area several prominent craters which make really useful stratigraphic markers when we're trying to figure things out. The youngest one is Hamilton Crater. That's the yellow area right here. It's been previously mapped, and this is the USGS Unified Geologic Map shown. This was previously mapped as Eratosthenian. Humboldt up here was dated to about 3.6 billion years in age. And that crater was later modified to have floor fractures as well as some volcanic activity. Right in the center here, we have Jenner Crater. This one's a little bit problematic. It's dated as Imbrian, but the ejecta kind of overlap and mess up some of the MARE in this area. So it's a little bit tricky to get CSFDs out of that area, which is unfortunately in the center of some of what we're interested in. And then to the south, we have Schrodinger Basin deposits. That basin was dated about 3.8 billion years. And you can see some of the rays and scouring marks that continue up into the MARE AUSTRALE area. And then they disappear in there. So they are superposed in there by many of the deposits, but some of the craters do actually predate that basin. So in the previous maps, two Imbrian aged MARE units were identified, and they're shown here in the pink and the reddish colors. And as I said, some of these are superposed by secondary craters from these prominent Jenner, Humboldt, and Hamilton craters in the area. And in the area also, besides the MARE deposits, there are a lot of light plains or smooth plains, and these include likely cryptomaria as well as basin ejecta type deposits. Previously, there has been some study of crater size frequency distributions and derived ages for these deposits, the MARE deposits in particular. This is the work that was done by Hiesinger et al. And that was largely using Lunar Orbiter 4, I believe, and some preliminary Clementine compositional information. And his mapped units are shown here in red. And they derived ages between 3.1 to 3.9 billion years for the MARE deposits. But you can see there's a big central area that's kind of missing any information. So it was hard from this data set to determine whether or not there were any trends across the proposed basin structures in terms of an age progression, because we're missing that information in the middle.
4 minutes.
Okay. And we were fortunately able to make use of the newer WAC and Kikuya terrain camera mosaics to look at morphologies as well as to derive additional CSFDs. And this is nice because it allows us to use the consistent illumination and scale of those products. So we have some cutoff diameters for the minimum diameters that we included in our analysis. So from the WAC mosaics, we cut it off at a 500 meter diameter, and for the Kaguya data set, 300 meters. But it's worth mentioning that some of these reached equilibrium diameter at diameters greater than those, and so we would use a different limit in those cases. So all of our areas were shown in pink on that image, but we're also looking for other clues besides just the CSFDs. We're looking for things like using the newer available compositional information to look for different flow units. So this is the familiar now Clementine UV-Vis iron map. And this is Lyo crater in AUSTRALE. And you can see in this map, there's two different units within this crater, and one is younger and more iron rich and more titanium rich than the older deposits. Some of the other things that we are able to do now are look for flow features and morphologies that were not previously resolved in the older data sets. So we have the goal of looking for potential interconnections between deposits, looking for possible pathways for flows, possible vents, and this is with the goal to help us constrain the number and volumes of eruptions that actually occurred.
2 minutes.
Okay. And this is an example of Barnard D here. And in this area, we have in the topography some potential flow paths as well as some morphologic indicators that there was probably flow between Barnard D and the surrounding areas. And that's consistent with the ages we derived of being just about the same for those deposits. So to summarize what we've been doing so far, we've been refining the number of flows and vents as well as the timing so we can understand this area better and its relationship to any basin structures. So far, our results show that volcanism in this area ended in the North AUSTRALE Basin area. So that's this area up here by Abel and Barnard D, and as well as in Humboldt crater. And that was about 3.4 billion years ago. There's lots of other volcanic deposits in the area, eruptions that mostly occurred around 3.6 and earlier. But this results in what's pretty much a really narrow range of volcanism, about 500 million years. And there's of course some earlier cryptomaria as well. But compare that to like Imbrium or SPA basins, where volcanism continued until about 2 billion years ago. So in that sense, AUSTRALE might indeed actually be a really good analog for early basin eruptions because we're not seeing those later deposits or later eruptions. So that's what I have for today. Thanks. I guess I can take questions. It looks like I might have a couple of seconds left.
Yes, thanks, Julie. So there is one question for you in chat from
Okay.
Catherine. Yes, and she asked, how would you differentiate volcanic flow features from impact melt flow features?
Oh, okay. That's an interesting question. For the most part, like it would be in terms of context. So melt flows generally occur with really close to the crater rim, but I assume you're asking about inside the crater, like a deposit in the floor. And for that, it's a little bit trickier. For most of these craters, we see that they have an iron enrichment that is stronger than what the impactor target would have been. So that's pretty much our assumption there.